Hello everyone, let's analyze. So today we're going to continue discussing Lagrange multipliers, and I have the theorem there just to remind you of the Lagrange multiplier result. Now, the Lagrange multiplier result gives us a first order condition. It says that if we have a solution to the constrained optimization problem, then certain conditions must be satisfied. Specifically, the gradient of the objective function is parallel to the gradient of the constrained equation. But if we find a value x naught that satisfies the Lagrange multiplier condition, how do we know whether it's a minimum or a maximum or just a saddle point? In other words, a place that satisfies the first order condition but is neither a min nor a max. Well, let's start by working out an example. So let's consider the case of a box with no top. Let me draw my pretty box here. Let's suppose that the depth is x, the width is y, and the height is z. And I want to maximize the volume. Of course, the volume would be a function of the dimension of the sides, and well, we know what the volume is. It's x times y times z. I want to make as big a box as possible. Of course, if this is all I had, I can make the box be infinitely big. So to make this a tractable problem, we have to have constraints. So constrained to the fact that my surface area must be of a given number of meters squared. All right, so what would be surface area given the fact that this box has no top? It would be x times y, the base, plus x times z, that's this side, and this side is the same size, though there's two of them. And this would be y by z, and there's two of those. So let us suppose that this is constrained to be 16 meters squared. This is an x here in case you can see. So using the method of Lagrange multipliers, I want to solve the gradient of v is parallel to the gradient of s, and of course s is constrained to be 16. So these would be my set of equations that would guarantee first order conditions. Right? It's what would be satisfied if I had an extrema. Okay, so let's solve this set of equations. Well, first I need to compute the gradient of v. All right, well here's v, so I need to take the derivative with respect to x, then y, then z. That'll give me yz, xz, and then xy. The gradient of s would be, let's see, I would get y plus 2z. When I take the derivative with respect to y, I would get x plus 2z. And the derivative with respect to z, I would get 2x plus 2y. So then this set of equations becomes yz equals lambda times y plus 2z xz equals lambda times x plus 2z, xy equals lambda 2 times x plus y. That's setting these two vectors to be parallel. And of course my last equation is xy plus 2xz plus 2yz, right? The surface area equation equal to my constrained surface area of 16. So I have 4 equations and I have 4 unknowns, x, y, z, and lambda. Now at this point, I could take all of my right hand side, subtract it to the other side, and find the root of a nonlinear function of 4 variables. Well, there are algorithms for doing that. In fact, I could apply Newton's method to this function to find the root. For those of you who have taken a numerical methods course, you're probably familiar with Newton's method. For those of you who haven't, don't worry, it's for now beyond the scope of this class. But just so that you're aware, that's typically what would be done at this process. Of course, typically you're working with much larger problems if we're working on an industrial scale. But just out of curiosity, what would that approach look like? Well, let's take a look. So if I wanted to solve my nonlinear equation numerically, I might write f as a function of x, y, z, and lambda, where f is the difference of my nonlinear equation because I want to find x, y, z, and lambda that makes f 0. I want to find a root of f. I would take the derivative of f, right, which you might call a Jacobian. This would be my derivative function here as a function of x, y, z, and lambda. And then I need an initial vector to start my Newton iteration. Now, I just picked kind of a random value for x and y. Well, I picked numbers. I picked 3 and 3, and then I solved for z so that my constraint was satisfied. Newton can be a fickle partner in solving nonlinear equations. In fact, if you ever get a chance to Google Newton basins, you'll find beautiful images that are crafted by the fact that Newton is, well, fickle. But if you start with something on the level set of your constraint, then you're likely to get better results. So I just kind of picked 2 values for x and y and found something for z to satisfy the constraint. And for my Lagrange multiplier, I just started with a random number. And then I began my iteration. And of course, if f is small enough here, 10 to the negative 10, I'll stop. And the Newton iteration is, of course, the older iterate minus the inverse of the derivative times my function evaluation. That's the Newton iteration in a nutshell, and we'll print out our data. So what happens? So here's my function at the end. It's of course on the order of 10 to the negative 10. It took 12 iterations to get there. And here's my solution, which is exactly what we would come to if we try to solve it by hand. But of course, why do it by hand if a computer can do it for you? Well, I guess because it's small and we can. But on industrial scale problems, this is the type of approach you'd want to use. And the optimal volume is approximately that. Now, suppose we did want to solve this by hand. Well, let's number our equation so we can keep track of what's going on. So this would be equation 1, 2, 3, and 4. Well, subtracting equation 2 from 1 means I would get z times y minus x equals lambda times y minus x 2z minus 2z. Of course, that part would be 0. Meaning that if I subtract this and factor out my common factor, I get z minus lambda times y minus x equals 0. Now, of course, one of these is 0, and, well, from our numerical experiment, we know which one. So either y equals x, right? That's if this term is 0, or I suppose I could say and or. Z equals lambda. Suppose y equals x. Well, then I could make this substitution into these 4 equations and, well, get a new set of equations with less unknowns. And of course, we want to reduce the unknown, just as a general rule of life. Well, from equation 1, I would get xz, replacing y with x, so I'm going to get rid of y, equals lambda x plus 2z. And my next equation, well, my next equation is exactly this. It wouldn't give us any new information, so we can leave it out. There's no reason to write this twice. Here I would get x squared equals 2 times lambda times 2x, so another 2 squared, and my last expression would give me x squared plus 2xz plus 2xz, so plus 4xz equals 16. So now we have a new set of equations. Let's number them again. So from equation 2, I would take this and subtract it to this side. X times x minus 4 lambda equals 0. Now, x, which equals y, cannot equal 0, because then my surface area would equal 0, and, well, 0 is not 16. So we can go ahead and divide by x, because x can't possibly be 0 and be a solution to our problem. So then this would yield x equals 4 times lambda. So let's take this expression of x and plug it into our now 3 equations. This would give me 4 lambda times z equals lambda times 4 lambda plus 2z. 4 lambda squared would be 16 lambda squared equals 4 lambda times 4 lambda, 16 lambda squared. Well, that's a tautology. It doesn't tell us anything useful. So in some sense, we've removed another equation as we've removed a unknown. And my last equation gives me 16 lambda squared plus 16 lambda z equals 16. So again, let's number our new equations. I'll number this one even though at this point it's pretty useless. So 1 would imply that 4 lambda z equals 4 lambda squared plus 2 lambda z. Take this and subtract it to this side. Subtract this as well while I'm at it. 2 lambda z minus 4 lambda squared equals 0. Now, lambda cannot be 0 because x, which equals y, equals 4 lambda. And as we discussed before, we can't have x and y be 0, then the surface area of the box would be 0. So I can divide through by lambda. And that would give me z equals 2 lambda. Well, I've eliminated another variable. Let's plug this into 3. All right, so this plugged into 3 gives me, I can divide through by 16 here, lambda squared plus lambda times 2 lambda, so 2 lambda squared equals 1 because I divided through by 16. 1 lambda squared plus 2 lambda squared, well that's 3. Lambda squared equals 1, meaning lambda is plus or minus 1 divided by the square root of 3. Okay, well, it cannot be negative because, well, x times y is quadruple it, and if lambda is negative, so is x and so is y, and then we no longer have a box with positive width and length, which would be a weird box. So since it's not physically feasible, we can discount that and just take plus 1 over square root of 3. And so x would equal y, which would be 4 divided by the square root of 3, and z from this expression would equal 2 divided by the square root of 3. And I have the dimensions of my box. Now, but what about letting z equal lambda from our first page of calculations? Well, I'll leave it as an exercise to show that this choice has no solution. Leaving this with the only feasible solution. So in the last example, I found a point that satisfied the Lagrange multiplier condition, but how do I know that it really represents a maximum of my objective function, which is the volume, subject to the surface area constraint? Well, let's consider this problem. Suppose f and g map an open set in Rn to R. Both are class CP, where p is at least 2. And suppose that I've satisfied the Lagrange multiplier conditions. Then have I found a maximum, a minimum? Neither. So let's define this h function, which is f of x minus lambda times g of x minus c. So we should note right off the bat that I basically have added to the objective function a scaling of the difference of the constraint. If x satisfies the constraint, then h of lambda x equals f of x. That extra term here is often called a penalty term. The bigger this term is, the more I do not satisfy my constraint. So if I take the gradient of h as a function of lambda and x, the derivative with respect to lambda is negative g minus c, and the derivative with respect to x is the gradient with respect to x is the gradient of f minus lambda times the gradient of g. So if lambda naught x naught is a critical point of h, in other words, if the gradient at lambda naught x naught is 0, then the Lagrange multiplier conditions are met and the constraint is satisfied, meaning that h of lambda naught x naught equals f of x naught. So to illustrate the idea, let's simplify the case to n equals 2. Suppose that the derivative of g with respect to x naught and y naught is not 0. Then the implicit function theorem implies that there exists an open set V containing x naught and an open set W containing y naught, where V by W is in the domain of the objective function, and a class CP function phi passing through the coordinates x naught, y naught, and satisfying the constraint. In other words, x comma phi of x satisfies g of those values is equal to my constant. Another way of looking at it is that the curve x comma phi of x is in the level set of g at c. So let f tilde of x be a function just of x. So it equals f of x phi of x. Right, so phi of x is my y value. I'm writing it as a function of x. And again, phi is implicitly defined by the constraint. In other words, this ensures that I'm considering the objective function where the constraint is satisfied. So if lambda naught x naught y naught is a critical point of h, then one can show that the derivative with respect to x of f tilde is 0, and the second derivative is equal to negative 1 over the derivative of g at x naught y naught, which we assume to be non-zero, squared. So this is a negative number, because again we're assuming this is non-zero. So this is a negative number times the determinant of the second derivative of h, right, which is what we can think of as this penalized objective function, evaluated at the critical point of h. Now, of course, if I take two derivatives of h with respect to lambda, I'll get 0. So that's why the 1, 1 entry of this second derivative is 0. If I take a derivative with respect to lambda and then with respect to the rest of x, I'll get the negative gradient of g. And then, of course, aside from this top and left border, then I'll just get the Hessian of h for the variables x and y. And of course, given the way h is defined, the Hessian of h is just the Hessian of f minus lambda times the Hessian of G. So this matrix here is called a bordered Hessian, because it's the Hessian with respect to x and y of H, bordered on the top and the left by the gradient of my constraint. So this allows us to write a theorem that describes what the second order conditions are for constrained extrema when specifically when n is equal to 2, or when f and g are functions of two variables x and y. So suppose I want to minimize or maximize f subject to the constraint that g of xy is equal to some constant, where f and g are both defined on an open set in R2. Both are at least C2 class. So if x naught, y naught is in the domain and is in the feasibility region, in other words, g of x naught and y naught is equal to C, and the determinant of the bordered Hessian, which, as we stated, is defined in this way, and we're going to call it, right, the determinant of this h bar for bordered Hessian, then if the determinant is positive, then remember the derivative of f tilde is negative, meaning that I have a local maximum. In other words, x naught, y naught is a local max. And if the Hessian is negative, then x naught, y naught represents a local minimum. And if the Hessian is 0, well then this second derivative test would be inconclusive. So let's give the second derivative test for constrained extrema in the general case. Consider the constrained optimization problem, min or maximize f, subject to the constraint that g of x is constant, C, where f and g both share an open domain in Rn, both are at least class C2. Now let x naught be in the domain and satisfy the constraint, in other words, g of x naught is C, and suppose the gradient of g at x naught is non-zero. Also suppose that x naught satisfies the Lagrange multiplier conditions. In other words, the gradient of f at x naught is parallel or a scaling of the gradient of g at x naught. Then if h is the penalized objective function we discussed earlier, in other words, h of lambda x is f of x minus lambda times g of x minus c, and h bar is the Hessian of this h. Where h bar is the second derivative of h. Of course, because lambda is a scaling, the second derivative with respect to lambda would be 0. If I take a derivative with respect to lambda, and then with respect to the rest of x, I'll get the negative gradient of g transpose at x naught as the top row. Similarly, I'll get it as the first column below the 0. And except for the top row and the first column, the rest is just going to be the Hessian of h with respect to x, or the second derivative of h with respect to the variable x, which would be a n by n matrix. And given the definition of h, the Hessian of h with respect to x is just the Hessian of f at x naught minus the Lagrange multiplier scaling of the Hessian of g at x naught. And so we call this matrix the bordered Hessian of the constraint problem. So if delta k is the determinant of the upper left k by k block, then if every delta k is strictly negative for k equals 3 through n, right, of course, for k equals to 1, I would get 0 because the top left entry is 0. For k equals to 2, I would actually get the negative of the second derivative of g with respect to the first entry of x squared. I'd actually get a non-positive number necessarily. So it's for k equals 3 and on that would matter. And if all of my determinant of these upper left k by k blocks are negative for 3 and on, then I would have a local minimum of the constraint problem. Now, if delta k has the same sign as negative 1 to the k plus 1, for k equals 3 and on, now again, that's a typo. That should say for 3 and on, then x naught is a local maximum point for the constraint problem. And if delta k are not all 0, but do not satisfy 1 nor 2, then x naught is a saddle point of the constraint problem. That is, it's a critical point that is neither a minimum nor maximum locally. So let's put this theorem to use. Let's go back to the first example we talked about today, maximizing the volume of a topless box such that the surface area of the 5 remaining sides sums up to 16. So if I computed the bordered Hessian, I would get exactly this. Now you may notice that if I take the gradient of V and the gradient of S and set them equal to a scaling of each other and add it to the set of nonlinear equations, the constraint S equals 16, and then took that difference, I want the difference to be 0. And if I took the Jacobian of that difference, I would exactly get the Hessian or a permutation of the Hessian, depending on which order I took my derivatives. In fact, in the example earlier, where we used Newton's method to solve that nonlinear set of equations, I had in my Newton's method exactly a permutation of this bordered Hessian. But now we're going to use the bordered Hessian to confirm that what we found really was a maximum, not some local minimum or some saddle point, but actually a maximum representing the max possible volume subject to this constraint. So we found that, or we conjectured that our maximum happens when x and y are both 4 divided by the square root of 3, z is half of that, and lambda is a quarter of x and y. So if I plug in x, y, z, and lambda into this bordered Hessian and computed my determinants of the upper 3 by 3 and then of the entire thing, what would I get? Well, I just happen to have it queued up here in MATLAB. You didn't think I was going to do it by hand, did you? So here I have my bordered Hessian as a function of x, y, z, and lambda. Here I have the x, y, z, and lambda values that I want to plug in. Here's where I plug them in. And delta 3 will be the determinant of the upper 3 by 3 block, and delta 4 will be the determinant of the entire thing. So if what I found was truly a maximum, then according to the theorem, I should be able to conclude that it's a maximum if delta 3 is positive and delta 4 is negative. So let's run this and find out. And in fact, I get delta 3 is positive, delta 4 is negative, and this is my bordered Hessian evaluated at the x, y, z, and lambda parts that we solved for. Confirming that what I found, or implying that what I found is indeed a local maximum. And because my function is defined for all x, y, and z that are positive, I can conclude that this is indeed a global maximum. Well, that's all for today.